So I'll come back to the second hour. Just to kind of recap briefly what we did in the first hour is that we came up with this one equation here in the red frame, which is an equation for V, which describes the evolution of linear disturbances, so small disturbances in a shear flow, in a viscous shear flow. And we have done that, or we have reached this equation by removing the pressure, or by replacing the pressure with a Poisson equation. And of course, because we used the Poisson equation, we suddenly now got fourth order derivative of V. But it's independent of anything else, and it's really just an equation where we have the time derivative plus some spatial derivatives, but all of V. And also what we see is that it's a homogeneous equation, which directly kind of makes it clear that this will, at the end of the day, will become an eigenvalue problem, where V being 0 would be one of the trivial solutions. But what we're talking about also is that in 2D, the V equation is sufficient because I can take the derivative and integrate it, so I will get a solution for U. But in 3D, I need something more. And this one more equation is the eta equation, or the equation for the wall normal vorticity, which we can also call eta. And you see the definition of eta here. And as I was just saying before, in 2D, so if I only have V and U, then eta is 0. Of course, that makes it nice, because if I have a 2D flow or 2D stability problem, I don't actually need to care about the eta equation. It's only if I look at three-dimensional disturbances where the eta equation becomes important. So in some sense, we can say that if you look here, du dz minus dw dx, so that means this eta essentially governs the horizontal fluctuations. Okay, so how would I now calculate the eta equation? Well, essentially, it's kind of the same principle as I have just done. You would again start from the U and the W equation. You would feed them into kind of vorticity form. You would remove the pressure. Everything that is not needed, you would remove. And so after so with substitution of the vorticity, substitution, and some algebra, as we have just done, so derivatives, etc., you will end up with this eta equation. As I said, I'm not going to do it here, but after some calculation, you will get the following: ddt plus ub times ddx minus 1 over Reynolds, nabla squared, and then you will have the eta here. But in this case, it's actually not a homogeneous equation. You have something on the right side, which is minus ub prime times dv dz. So this is then the corresponding eta equation corresponding to the v equation that we had above. So also just putting that in the frame. So now I have these two equations, one for V and one for eta, and together they would now describe the complete system for the evolution of linear disturbances. So there's a few comments that I would like to make in addition to what I have written before. So, or maybe like this. So these two equations form a complete system to describe the evolution of linear disturbances in a viscous shear flow. So apart from the assumptions in the beginning, where we said it's a parallel flow and it's linearized, we have not done any more approximations. This is really kind of the linearized Navier-Stokes equations for the parallel flow. And what you can see now, if you look at these two equations, you can see that the V equation is independent and the eta equation depends on V. So if you think of the sequence of how to solve that, it would be first you would solve the V equation, you get a V disturbance, and then you would take your V and put it into the eta equation and then solve the eta equation. So we can kind of say that the dynamics of V is independent of the eta equation. So I can solve it first. And of course, as a consequence, the dynamics of eta is actually dependent on V, or one can also say is forced. So there's a force that goes in here on the right-hand side of the eta equation. So it's forced by the dynamics or by that of V. So eta is not independent of V. So that means we may want to actually try to understand a little bit better what this strange term is, or what it actually does. So let's look at that. So the term is like this: UB prime dV dz. And this term appears as a source term in the vorticity. So what could that be? Well, if you think back, I don't know, 5-6 hours, when we talked about the vorticity equation, we realized that the vorticity equation essentially is an advection diffusion equation with one more term. And this term was the vortex stretching and vortex tilting term. Right? And this term here essentially is exactly that. Because if you look at the if you look at this is just a kind of advection diffusion equation. So we have the advection here, we have the diffusion here, plus something in addition. So in the end, you can view this as the linearized version of a vortex stretching or vortex. In this case, it's a vortex tilting term because the derivative, it's not on the diagonal, it's kind of an off-diagonal term. So this would be a vortex tilting term. So this is vortex tilting term, which then acts as a forcing, as we were saying. It acts as a source term in the vorticity equation. So what does it really do if we now try to sketch as we did it at the time, so that we understand, what is actually tilting in what direction? So if you have a coordinate system x, y, and z, and we know from our assumption from the beginning, when we said that it's a parallel flow, so that the mean velocity is u as a function of y. So we know that our mean velocity profile is actually just something like this. So this would be our base flow, ub of y. So now the question is, what is actually tilting in what direction? Well, so what components do we have here in this vortex tilting term? So we have here the ub prime. So that would be the shear in the vertical direction. And dvdz. So dvdz would be the span-wise change of v, which is then somehow multiplied by the base flow and creating wall normal vorticity. So in a sense, we can now write that the span-wise change, so that's dv dz, will kind of be tilted. We will see now in a second what is actually tilted. Will be tilted by this term into vertical vorticity by the mean or the base, let's say base shear. So the span-wise change of dv dz, this you can also view as essentially streamwise vorticity, because if you have the flow going like this, and you have v changing as a function of z, this essentially corresponds to streamwise vorticity. So this span-wise change dv dz, this would be streamwise vorticity. And this streamwise vorticity acts as a source term in the wall normal vorticity term. And of course, what happens is that the base flow, which is shearing in the vertical and the y direction, is essentially tilting up the streamwise vorticity into wall normal vorticity. So in a way, it's not so easy to sketch this, but if I had kind of streamwise vorticity like this, and I have the base flow acting in the way that I sketched here, it's essentially that these vortices are kind of upwards tilted by the action of the base flow. So this is how you can interpret the vortex tilting that goes on in this inhomogeneous term in the eta equation. So it's nothing else than a vortex tilting term in the linearized setting, which takes span-wise variations of v and creating a source in the eta equation. So in that sense, everything is consistent. We looked at a vorticity equation, and of course, as a consequence of vorticity equation, we have a vortex tilting term, and that's what it does. And of course, again, if we then realize the fact that in 2D we don't have any vortex tilting, actually we don't have these span-wise changes, and of course that means that in 2D all of this equation is zero. The vortex tilting is zero, and of course that means also that eta is zero, and it will remain zero. So there's no way of creating eta in this case. Okay. So that means what have we obtained right now? We have the V equation and we have the eta equation. And as I wrote here in red, these two equations form a complete system for the evolution of a viscous of linear disturbance in the viscous shear. What would be the next step? What else do we need to do? If you now think back on our little example that we had in the very beginning for stability, what is missing now? Or why can't we solve it yet? Or maybe the question is different. What do we want? Well, we wanted to have kind of this eigenvalue problem in terms of an eigenvalue which gives us exponential growth or exponential decay. So that means somehow we need to bring in something that grows exponentially. And of course, the way to do that is to perform a Fourier transform, as we were doing at the time. So we somehow need to bring in an exponential ansatz for our V and eta disturbance, so that we can actually have this the split into space and time, and then we can formulate the eigenvalue problem. So that's now the next step. And I would call this now the step of linear stability. for this step. So we take the perturbation equations, but we actually introduce this Fourier decomposition so that we can calculate eigenvalues. So what I will do here is in the derivation, I will focus on the V equation. But you can do exactly the same approach also for the eta equation. But I'll just focus on the V equation, which means that actually we're looking at 2D disturbances. But as I said, there's no problem in extending that to 3D. So that's one approximation, and the other one is that I'm using, or I will be using specific boundary conditions, particularly U, V, and W being 0 at walls, so wherever I have solid walls. And of course, that means then translated this to a V and eta formulation, because U and W, of course, don't appear anymore. But then I have V and eta being 0, and also, that's important, d eta dy being 0 at walls. Okay. So now having this, or having said this, now I'm going to use my Fourier ansatz. And this is what is typically called in the literature a normal mode ansatz. But it's nothing else than essentially a Fourier ansatz. Normal mode in this sense, or in this setting, just means that I do an ansatz in a bunch of modes that are orthogonal to each other, or normal to each other. So that means my V, which used to be a function of x, y, z, and t, I will approximate, as before, as the real part of some v hat, so a Fourier coefficient, as a function of y, times e to the I, and then I need to get all the spatial dependencies, so x and z. So I have alpha x plus beta z. And then I have also the temporal dependency minus omega t. Now, you may wonder now about a few things. So first of all, the way that I'm writing it here, that's kind of convention, that I'm taking out the I. So what I have left here is alpha times x plus beta times z. So these are the spatial dependencies. And it may look a little bit inconsistent that I'm having here alpha times x, which is then the x dependence, but then I'm having beta times z. I guess more consistent would be gamma times z somehow, because b would be the second letter, which would then be in the vertical direction. I cannot say why this is like that, but the span-wise wave number, the beta here, is just called beta. It's inconsistent, I understand, but that's just what it is. So that means the beta here corresponds to the z dependence, and of course the y dependence, so the dependence in the direction in which I have my shear flow changing, this is kept as the dependence of the Fourier coefficient, so the v hat here. So I have in x and in z, or in alpha and in beta, I do a Fourier approximation, and in y I keep the Fourier coefficient variable. And then finally, I have the temporal dependence with a minus sign in the front, so minus omega t. This will give me this temporal dependence. So this is the standard way of writing the normal mode ansatz for. And of course, based on this, we can now. So, yes. Why is the time dependence negative? That's convention that we write it in this way. Yeah. I will show it afterwards. Or I can directly show it now. So the basic idea then would be that you could write it as a wave. If I'm just taking now x and t, you would essentially then get this the typical wave ansatz that we have already used for the Stokes second problem, where if the waves look like this, then this distance here would be 2 pi divided by omega, and this guy, the wavelength, would be long, so this would be the period, and the wavelength would be 2 pi divided by alpha. And if I'm having it now with a minus sign, so alpha x minus omega t, it would correspond to waves that are in this way. Otherwise, they would be switched. And the reason for this is that this would correspond. So if you're standing at this point here, for instance, in space, and you will just see what happens as a function of time. You would see a wave coming from minus x going to plus x. So it would kind of pass in the positive direction by you. That's why it's like this. But of course, as you, what you can do now is you can, as before for the Stokes problem, we can define a wave speed. That would be c times omega divided by alpha. So that's the speed, how quickly one of those wave crests would be passing by. And of course we have the alpha, which is just 2 pi divided by the wavelength lambda. So lambda would be the wavelength, and alpha would be the wave number. And in time, it's the same thing. You have omega being 2 pi divided by t, where t would be the period of the wave, and omega would be the angular frequency. And of course, beta would be 2 pi over, if this is lambda x here, would be a lambda z, and lambda z would again be the wave length, but in this case in z. Okay, so this is now the wave ansatz that I can use to transform my disturbance equations from V into an equation for V hat with all these Fourier coefficients. So, so what I can do now is substitute everything, or not everything, but the wave ansatz into the evolution equations. So I'm just taking this V here and I'm plugging it into I'm just plugging it into the V and the eta equation. I mean, the V equation, if I want to do 2D, in 3D, I would also put it into the eta equation. And of course, the thing is that suddenly derivatives in x and in z, they will then just become multiplications with the wave number. That's the beauty of this. Derivatives in y, they of course will still remain as derivatives of y, but it will be derivatives of v hat. So just this space function, or this the wave function, which is only a function of y. So that means partial derivatives will disappear, and it will be only ordinary derivatives being left. So if I'm doing that, and I'm not going to do that step by step because it's slightly boring to do so, but if I do that for both the V and the eta equation, the result will be minus I omega plus I alpha times I alpha times UB, UB times d squared minus k squared minus I alpha UB double prime minus 1 over Reynolds of d squared minus k squared squared times v hat is 0. Okay. Now I need to explain that a little bit. So again, what I wanted to do is I just took this normal mode ansatz from here and I plugged it into the V equation. Now, if you just stay here with this term here on the first term, we have a time derivative and we have the UB times ddx times nabla squared. So how did this turn out to be here? Well, the time derivative obviously is something with like minus I omega, kind of makes sense. The space derivative has become I alpha times UB. That kind of also makes sense. And then before we had the multiplication with nabla times V. Nabla is a second derivative. And this has now become here d squared minus k squared. So what is d squared? Well, d squared somehow is an operator that acts on v hat. So in a way you can say that d squared is just shorthand for the second derivative operator. So consider it as d being the first derivative in the vertical direction, and d squared obviously will be the second derivative, because you just apply the derivative twice. So this is shorthand for the derivative operator. K squared, at the same time, that would be the total wave number. So in this case, it would be a squared plus alpha squared plus beta squared. Now, why does this appear here? Well, this is essentially, if we look here again in the original term, that would be the second derivative in the x and the z direction. Now, the y direction we have now taken care of with the d squared, but then we have the x and the z direction. Of course, in Fourier, the x direction, or derivative in x, would be I alpha times I alpha, and I alpha squared gives me minus alpha squared, and the same in beta. So therefore, this bracket here would just be, so this bracket here would just be the nabla squared times e. So d squared minus k squared. And now, of course, we can also look at the other terms. So the next term is this is the wrong equation here, minus ub double prime times ddx. Well, that's this one, ub double prime ddx is minus I alpha. And then we have the viscous term, which is the fourth derivative here, minus 1 over Reynolds nabla to the 4. And here this becomes minus Reynolds times this nabla squared operator, d squared minus k squared squared. So that's kind of the principle on how we obtain this equation now in Fourier space. And as I said, notationally, the vertical derivative is called d, and the whole parallel derivatives are approximated with alpha squared or b plus beta squared if you take it in both directions. It's alpha squared plus beta squared. So this here is now my my transformed or Fourier transformed equation of V. Now I can of course do exactly the same trick for my eta equation, this one here, and I can also directly write down the result here. Maybe I do it. I just move this a bit down. So first the equation. So I'll get here minus I omega plus I alpha ub. And now there's no derivatives of eta. There is nothing here for the base flow, just the viscous term minus 1 over Reynolds, and this is actually the same, d squared minus k squared. And this is now times eta hat. So again, eta hat would just be the Fourier coefficient of eta. Now there is one difference, because here we have not a non-unitary, an inhomogeneity. So we have something on the right side. So that means we need to have here minus I beta ub prime times b hat. Okay. So these two equations, so the first one for V and the second one for eta, are the Fourier transformed evolution equations for my disturbance. So these are the equations for V hat and eta hat. And these two actually are very important equations because these were exactly the ones that were derived for the first time, in 1910 by two people independently, by Ohr and Sommerfeld. So these are what we call the Ohr-Sommerfeld equations. And the second one, the one for eta, came a little bit later, and this was derived by a person called Squire, and therefore these are called the Squire equation. But these two equations are really the fundament for any type of linear stability calculations that we do. So these are the Ohr-Sommerfeld and the Squire equation. Of course, as usual, I would like to tell you also the people behind it. So the Ohr-Sommerfeld equations were derived by William Ohr, who lived 1866 until 1934. And then we have Sommerfeld, which is Arnold Sommerfeld. And he lived 1868 until 1950. And then we have Squire, which is Herbert Squire. He was a little bit later. He lived 1909 until 1961. And we will meet again Squire later on when we talk more about some of these solutions. So the Ohr-Sommerfeld equations, they were, as I said before, they were developed independently by Ohr and Sommerfeld. I guess it was Ohr that was maybe 1 year earlier. He published it. It was not really widely spread, his publication. So Sommerfeld was then deriving them again. But Sommerfeld was then also realizing that later on that Ohr has already derived them a little bit before. So there was no real dispute here. But nowadays they're really known under the name Ohr-Sommerfeld equations or just the OS equations. And the Squire equations, they, as I said, they came a little bit later. I think it was actually 1930, if I is correct. No, it's not written here. Yeah, I think it was 1930 when the Sommerfeld, where the Squire equations were derived. There is a reason for why the Squire equations are maybe not so important as the Sommerfeld equations, and the reason for that is because they're forced from the V equation. It actually turns out that any instability must come from the Sommerfeld equations. And of course, if you have an instability in V, you also may have an instability in eta, but it cannot be the opposite, that you have an instability in eta, which will then cause an instability in V. So therefore, anything that is unstable actually needs to come from the Sommerfeld equations first. Okay. Yeah. So these are now the governing equations, and there is because they're so important. There's kind of a yeah.
Can you hear me?
Yes.
I have a question, maybe stupid. Why the exponential doesn't appear? I mean, our answer.
Okay, I think I know what you mean. So the exponential, you mean I guess you mean this bit here, this one.
Yes.
Yeah, this doesn't appear because it would appear for all the terms. So you can actually divide by it. Because if let's take the example here of the V equation. What we would do is we would put in this exponential, so the V hat times e to the whatever as instead of the V here. And then of course it would mean that we can then go in, do all the derivatives, but because the derivative of an exponential is the same exponential again, times some of the inner derivatives from the chain rule, in the end, each term would have this exponential in it. So you can just divide by it. So what you're ending up with is an equation in terms of the Fourier coefficients, all the exponentials that you can divide with. Which of course then also means if I want to go back from V hat to V, so if I would like to see my disturbance in physical space, of course then I need to put back in the exponential to see the variation in both alpha, beta, and omega. Okay, so I have now these equations, and as I said, because they're so important, there is also kind of a standard matrix way of writing those. And this we do like this, that essentially we realize that there is a matrix times a vector, which is equaling a right-hand side. And of course, the unknowns would now be V hat and eta hat. The inhomogeneity would be 0 and 0 here. But then in the coupled system, we will have here what we call the Sommerfeld operator, and a 0 here. Then here we have a C, and we have the Squire operator. Now, let's try to identify what this is. So I guess now we can see everything. So the Sommerfeld operator is essentially whatever multiplies V, which would be, in this case, kind of this whole thing. This would be the Sommerfeld operator times V hat being 0. On the Squire side, on the Squire side, L, also the Squire operator times eta, that would be this bit. And then we will have the C here, which would be whatever is multiplied with V hat on the second row, which is this bit here. So in this way, we can write both the Sommerfeld and the Squire equations together in one matrix system, which is then suddenly homogeneous, because the inhomogeneity of the Squire equation is actually it's multiplied with, or is a function of v, so therefore it appears in the matrix. So this is kind of the standard way of writing the Orr-Sommerfeld square system. So Orr-Sommerfeld slash square system. And it's actually a homogeneous system. So, and in order to be able to solve this, I need to have boundary conditions, and now I can go back to what I said earlier, namely that v hat should be the same as dv hat and eta hat being 0 at walls. And, well, in the end, this is now a system that I can solve, because I just need to formulate my Orr-Sommerfeld operator, I need to formulate my C, I need to formulate my square operator, and then I just solve it or supplement it with boundary conditions, and then I solve it. So that actually makes that is a nicely well-defined system which I can solve. And what I get from it is v and eta, and then when I have v and eta, I can calculate u, I can calculate w, and I can visualize my solution. But of course, the problem now is, so what is it really that I would like to solve? And of course, as we said earlier, in the end, this will turn out to be an eigenvalue problem, because as you can see, the trivial solution for v and eta, just v and eta being 0, is of course a solution for it, but this doesn't help very much. So we have a trivial solution, and this trivial solution is simply v hat being eta hat being 0, and that's also nicely consistent with the boundary conditions. But more interesting solutions would come out when I'm actually considering the situation where the determinant of this matrix, so LOS 0 C L square, where this determinant would be 0. And of course, that's exactly then an eigenvalue problem. Now, if I'm talking about an eigenvalue problem, of course, there needs to be an eigenfunction or an eigenvector and an eigenvalue. And, well, in the standard setting and also the setting that has been used for the first time, we would say that omega, so my temporal frequency, would take the function of an eigenvalue. And this is what is called a temporal problem. The temporal problem for alpha and beta fixed. So that means in my expansion that I introduced before, I will have it here. In this expansion for the normal modes, I would say that alpha and beta are given numbers. They determine, or they state, what is my wavelength in x and what is my wavelength in the spanwise direction. And omega, so the temporal dependence, would then be the eigenvalue, which could either grow, decay, or it can oscillate. So that means my omega, in that sense, would be a complex number. So it has both an oscillatory part and a growing part. So that means my omega would actually be omega r plus I omega I. Of course, that means that my e to the minus I omega t would have two parts, e to the omega I times t times e to the minus I omega I times t. And now in the spirit of what we did last time, we can identify two different components. The first component in this case would be the growth rate, because it's an exponential of just omega I times t. And the second part would be an oscillation. Yeah.
It shouldn't be e to the minus I omega e r.
Yes, of course. This should be an omega r. So, yes, I'm sorry. Yes. I guess the important thing here is to realize that the growth rate is actually the imaginary part in the way that we formulated it, and the oscillation would be the real part. And of course, that kind of also makes sense that if we think of an omega as being kind of a number times hertz or whatever, 2 pi over second, then the real part of that would just be the normal oscillation, and the imaginary part would then determine whether it grows or not. So omega r here would be the angular frequency. Okay, I guess we take a break, and then after the break, we will look at a few examples of that. So we'll actually go in and look at those solutions and try to understand what these solutions actually mean, or how they translate to the physics of a problem. Okay, let's have a break now.